Moving along to the next page, we are about to begin a very long and very detailed discussion of what is possibly the most important aspect of quadratics and quadratic functions and quadratic equations that you'll need to know for this test, and that is the concept of zeros. We need to know quite a bit about the zeros of a quadratic, what they are, how we find them, what their significance is when it comes to quadratic models. So we are going to be talking for many pages about the zeros and all of that stuff I just mentioned. Let's go ahead first of all, though, and talk about what it means to talk about the zeros of any function, not just a quadratic, but any function. Again, this is a concept that all sophomores, juniors, and seniors have seen over and over and over again, and yet many times when we ask a student to verbalize to us what a zero of a function is, students are very hesitant. They have a very difficult time doing that, verbalizing what a zero is. It is important that you are able to give a nice, clear, confident definition of the zero of a function. So let's go ahead and write that definition down. The zeros of a function are going to be the input or x values, that make the output, otherwise known as the y/f of x values or value, equal 0. This is not a very difficult concept, but again, a lot of students are hesitant about defining what a zero is. I'm going to look at a linear function real quick. If I write y equals 2x minus, let's say, 6, well, I can see that when x equals 3, this side of the equation, the right side of the equation, becomes 3 times 2, 2 times 3, 2 times x, minus 6 equals 0. So 3, that input or x value, produces an output or y value of 0, and therefore 3, that x value, is a zero of this linear function. So again, that's all a zero is. It is an x value that makes the y value equal 0. In example 1, we are going to evaluate a quadratic function at a couple of different values of x. We are not going to be using our calculator for this. Something like this is perfectly likely to show up on the no calculator section, so we are going to do this without a calculator. So what we want to do is we want to evaluate f of -1. Remember that parentheses, what's in that parentheses is an x value, this notation f of x. Inside parentheses we have an x. So that -1 is an x value. So what I'm going to do very carefully here, I'm going to write down, let me zoom in a little bit, I'm going to write down -1 squared minus 3 times -1. Notice I'm putting everything in parentheses so I don't make any careless mistakes. This is all going to end up equaling 1. That's -3 times -1, so that's 1 plus 3 minus 4, and of course that's 4 minus 4, which equals 0. Now, if I evaluate the same function at an x value of 4, what I get is, and again, I'm going to, even though there's not a negative here, I'm still going to be very careful. I'm going to put that 4 in parentheses so I don't make any careless mistakes. And what do I get here? I get 16 minus 12 minus 4, which also equals 0. So when x equals -1, my y or f of x equals 0, and when x equals 4, my y or f of x equals 0. That means that these two values of x, -1 and 4, are the zeros of this function. They are, in fact, the only zeros of this function, but these are the two x values that will produce a y or f of x value of 0. Therefore, those two x values are the zeros of this function. X value goes in, 0 pops out. That means that x value is your, or are your zeros. By the way, if you look back at the parabola on the previous page, we have x squared minus 3x minus 4. That's exactly the same quadratic function that we were dealing with in example 1 here, and you can see that this parabola hits the x-axis at the points -1, 0 and 4, 0. And if you recall, those were the pairs of numbers, -1, 0 and 4, 0. Those were the pairs of numbers that we got when we evaluated this function at -1 and 4. That is not a coincidence. When we talk about the zeros of a function, those x values, we are also talking about the points at which the function, or I should say the x values namely, at which the function will intersect the x-axis, the points at which the parabola that the function corresponds to will intersect the x-axis. So zeros are indeed synonymous with x-intercepts. There's really no difference between those two terms. In fact, there are several items that we need to understand are synonymous with or related to zeros. This box will be extremely important in your understanding of quadratics and in our discussion of quadratics here. We need to understand that when we say n is a zero of some function f, so n is just some x value, and if we say that x value n is a zero of f, all of these 6 items are also true. F of n equals 0. In other words, when n goes into the function, a 0 comes out. When the input is n, the output will be 0. When x equals n, y equals 0. Those are just 3, 4 different ways of saying the same thing. Root and solution to a quadratic equation, those are also synonymous with zeros. So we would say if n produces a 0 when n goes in, the output is 0. We would also say that x equals n is a root of the quadratic. We would also say, we already talked about this a moment ago, that n, 0 is an x-intercept of the graph of f. We would also say, we're going to get into this a little bit later, that x minus n is a factor of f. So if I know, for instance, that x equals 2 is a 0, I would know that x minus 2 is a factor of the polynomial function that I am dealing with. Divisibility and remainders are not going to be all that important. We will go over this a little bit later. But in the same way that when I say 3 is a factor of 12, 3 is a factor, of 12, I could also say that 12 is divisible by 3. I'm just sort of flipping around the framework there. Well, in the same way that I can say that x minus 2 is a factor, x minus 2 is a factor of some function f, I could also say that f is divisible by x minus 2. With the remainder issue, we will talk about this later. There's no need to get into it now. But again, as of this point, it is important that you have some sense of all of these items, how they relate, namely the fact that they are pretty much synonymous with each other. And if you are given one of these, you can assume all of the others are true. So if I know that n, 0 is an x-intercept of some polynomial function's graph, then I would know that n is a root. I would know that n is a 0. I would know that when n goes into the function, I get 0. I would know that x minus n is a factor of f, all that stuff. Finding zeros. We have to talk about all of the ways that we can find zeros. There are many of them. Probably the easiest is having the graph of the function and just looking at where that function intersects the x-axis. Remember that when we are on the x-axis, the y-coordinate is always 0. This point, this point, this point, this point, this point, this point. All of these points on the x-axis will have a y-coordinate of 0. In fact, the equation of the x-axis, this might surprise some of you, the equation of the x-axis is y equals 0. The equation of the y-axis is x equals 0 because all of the points on the y-axis have an x-coordinate of 0. So when a graph intersects the x-axis, we know that our y-coordinate is 0. I guess I'm going ahead and doing example 2 right now. And this guy is going to be something, 0. So all we have to do is determine what the x value is at that point. And of course, this point on the left, it's -1, 2, 3, 4. So that's -4. And on the right, this is, let's just say, approximately 1/2, and that is what the question asks for. We should circle that. The approximate zeros of this second degree polynomial will be -4 and 1.5. I should actually put a and between there. So x equals -4 and x equals 1.5. Those would be the two zeros. In case it's not clear, all we are doing there is looking at the values of x where the graph intercepts the x-axis, and that will give us our zeros. The x values at which the graph hits the x-axis will also be the zeros or roots of the function. Moving along, at the top of the next page, we're going to do another example similar to the one that we just did. However, in this case, we are using an example that will demonstrate that finding the zeros and or the factors of a polynomial function from a graph is the same no matter what kind of polynomial function you're dealing with. If you're dealing with a quadratic or you're dealing with a cubic, which is a third degree polynomial function, so if your function is an x² function or an x³ function, it doesn't matter. When we look at the graph, and by the way, this actually applies to all functions, even exponential functions, logarithmic functions, it doesn't matter. If we are looking at the graph and we can see where that graph hits the x-axis, where that graph intersects the x-axis, we are looking at the zeros of that function. We are looking at the values of x where the y value is 0. So in example 3, you can use your calculator here, but it will not help you at all. There is really no way to use your calculator to answer this question. So in example 3, we have a third degree polynomial graphed on the xy plane above, and we need the linear factors of the function. Well, you'll recall in our little info box on a previous page, we said that when x equals n is a 0, we knew that x minus n is a factor of the function. So that's what we are going to need to know for this particular example. We should be able to see that our zeros are at these 3 points. So what are those 3 points? That's -1, 2, 3, 4, 5, 6. So that one there is x equals -6. It is the coordinate -6, 0. This one here should be pretty obvious that is x equals -1. So that's -1, 0. And then this one over here is 1, 2, 3, 4. X equals 4. And that is the point 4, 0. So if I'm taking my zeros of x equals -6 and x equals -1 and x equals 4, and I want to convert to my factors, well, remember, all I really have to do is put an x minus in front of those zeros. So x minus -6, x minus -6, remember that just becomes x plus 6. So there's one factor. Same sort of thing here, x minus -1, that's just again x minus the value of the root or 0 there, and that becomes x plus 1, and then x equals 4, that's just going to be x minus 4. So our 3 linear factors of this cubic function, of this third degree polynomial function, they are going to be x plus 6, x plus 1, and x minus 4. Those are the 3 linear factors of this cubic function. Keep in mind that parabolas do not need to cross the x-axis. Parabolas actually can touch the x-axis at only one point. So we've seen a couple of parabolas that look like this, but remember that parabolas can also come down. They can touch the x-axis. In other words, the vertex can lie right on the x-axis. Some parabolas will not touch the x-axis at all. We are going to discuss all of these variations, all of these possibilities. However, we should know that for parabolas that are tangent to the x-axis, in other words, something like this, those parabolas, the quadratics associated, the equation associated with those quadratics will always be able to be written in a particular form. In fact, our p of n function that we looked at on page 133 that was p of n equals negative 3n minus 5 squared. This p of n function, we actually have it written in the form that we need to be aware of. All parabolas that touch or are tangent to the x-axis can be written in the form y equals a parentheses x minus h squared. And a couple of important things here. Obviously, the x and the y are just our regular old x and y. The h, the thing that's in this position, is the x coordinate of the vertex. In other words, it is the x value at the point of tangency. So we can see that in this case, we've got n minus 5. That's like x minus h. So we should be able to see that the h would be in the, that the 5 would be in the h position. So 5 is h. And indeed, if we look at that graph of p of n, we should be able to see that p of n intersects the x-axis at 1, 2, 3, 4, 5. So indeed, that 5 would be, or would correspond to, the point at which, the x value at which the parabola will intersect the axis. The a value here, the a value that's lying here in front of the parentheses, we can determine what our a value is by substituting a known point on the parabola. That is usually the way we'll determine what the a value is. We're going to try this on example 4 right now. So on example 4, you can see we do have a parabola that hits the axis, that is tangent to the axis at only one point. It does not go above and then below, as a couple of the parabolas we've already seen do. So let's go ahead and read through this question. If you want to try the question on your own, as always, pause the video, try the question on your own, and then come back and join us. The equation of the parabola graphed above is y equals ax minus c squared, where a and c are constants. Okay. If the parabola crosses the y-axis at y equals negative 8, what is we need the product of a and c. That's what we're looking for. So remember that we said that all parabolas that touch or are tangent to the x-axis can be written in this form: y equals ax minus h squared. So why don't we write that down? Let's write y equals ax minus h squared. Remember what we said about the h. The h is the value at which, the x value at which the parabola hits the x-axis. So in this case, our h is negative 4. I'm going to put that in parentheses. And we still don't know our a value, so we're going to write that a out there. So at least now we know part of the structure of the equation of this parabola. And of course, we also know now that our c value, which is this guy here, we know that that c value is that negative 4, right? X minus h, they're just changing the h to a c. That's fine. We said that that h was negative 4, so that c is negative 4. I'm going to actually write that down. I'm going to write it over here. C equals negative 4. I don't want to forget about that. In order to find that a, we've got a little bit of a problem because we've got 3 unknowns. We've got a y, an a, and an x. Remember that we need to get rid of 2 out of those 3 unknowns and be left with only 1 unknown in order to solve for that unknown. Well, we actually have a value of y and x here. It might not be obvious, but this piece of information gives us a value of y, obviously, but it also gives us a value of x because we are being told that this parabola crosses the y-axis at y equals negative 8. And we know from a couple pages ago and from everything we've been doing in our geometry classes and a lot of other classes, we know that if we are on the y-axis, our x value equals 0, right? That's what a y-intercept is. It is the value of y when x equals 0. So when they tell us that a parabola crosses the y-axis at y equals negative 8, they actually are in effect telling us that the point 0, negative 8 is on this parabola, which means 0, x equals 0, and y equals negative 8 must satisfy the equation of the parabola, which also means we can now do this. Negative 8, I'm just substituting that y value in for y, equals a parentheses 0, I'm just substituting that 0 value in for x, plus 4 squared. And now this is just a very simple basic algebraic equation. 0 plus 4 is 4. 4 squared is 16. So I've got 16a. I'm going to divide by 16. I'm writing all my intermediate steps here. I've got a equals negative 1/2. Just flipping the two sides there. This is a calculator question. If you wanted to use your calculator to solve any of this, you could. I did not, obviously. So we have that a equals negative 1/2. What were they asking us for the product of those two things? The product of negative 4 and negative 1/2. I don't know why I put a comma there. Let me put a multiplication. Negative 4 times negative 1/2, of course, is positive 2. That should be the product of a and c. So that is how we would go about constructing a equation for a parabola that touches the x-axis and figuring out what a couple of those constants involved in the equation are. We are, again, going to go over some parabolas that do not touch the axis at all. You should know for the time being that if a parabola does not touch the x-axis at all, then that quadratic's roots are imaginary as opposed to real numbers. If the parabola touches the axis, as it has in most of the examples we've already seen, the quadratic's roots or zeros are real. If the parabola does not touch the x-axis at all, then the quadratic has only imaginary roots.